Okay, on to part 2 of rotation mathematics. So before we go into it, let's talk a little bit about inverse matrices. The inverse of a matrix has the property that if you multiply the original matrix by that inverse, you will get the identity matrix in return. Simplifying it a bit, but I think that's a pretty accurate description. So let's jump into this cool little video interactive.
So now we're going to find the...
Actually, no. I'm going to leave this in the lecture. This is quite long. It's going to go through inverse matrices. I think if that's something that you need to brush up on, valuable to do. So please feel free or go to this YouTube link down below. We're going to breeze through this because we're assuming that at this point you've had enough exposure to linear algebra that you understand how to determine an inverse matrix or know the various Wikipedia articles to read to load up on Google to figure it out. So the inverse of a matrix has the property that if you multiply it by the original, you'll get the identity in return. Here's an example of a really simple one, right? 0, negative 1, 0, 1, 0, 0, 0, 0, 1. The inverse of that being actually the transpose. So if you flip them and if you multiply those, you'll find that the answer is going to be equal to the identity. So here's an example of that multiplication, that math. And out of that, really quickly, you pop out and you see that there's the identity matrix, a 3x3 identity matrix. So in this case, actually, this was a rotation matrix. As you can kind of see that this is a rotation about 90 degrees, given that it looks like it's about 90 degrees in the z-plane. You can remember cosine, negative sine, sine, cosine, and so in this case cosine of 90 degrees is 0, sine of yeah, no, yes, I forget, yes, cosine of 90 degrees is 0, sine of 90 degrees is 1, I know math, yeah, and so you can see this would be the equation. In this case, if you take a respective rotation negative, the cosine of theta is equal to the cosine of negative theta because it's 0. So if we do this for 30 degrees, you can see that the values kind of pop out where you get this sort of opposite effect. Again, that keeps in the diagonal and then flips it around. And then if you multiply these two by each other, you'll see that you'll get the identity matrix in the diagonal. So this kind of takes advantage of the property that cosine of theta is equivalent to cosine of that negative theta. And it actually looks very similar to the previous one, but you also notice that the rotation in positive 30 degrees is the transpose of negative 30 degrees. And so we'll talk about this more later in this, but some matrices, their inverse is going to be equal to their transpose. And that's pretty common with, that's the case with rotation matrices, which is a very useful property. So in this case, we're just kind of forcing it. We know if we rotate in 30 degrees, we expect the opposite to be if we do it in negative 30. And so we can see out of this, we get the identity matrix. Cool. So let's do this again. In this case, we'll do it for 60 degrees. And we can see that similarly, we again get the 60 degrees. Cosine of 60 degrees is 1/2 or half, 0.5. And again, we get this sort of transpose effect. And if we do the math here, we see that out of that pops out the identity matrix, which is what we expect to see. If you rotate in 60 degrees and then negative 60, you want to be back where you started. So let's do this again for 90. And you can see it's exactly what we expect. And the numbers here are quite simple. So let's do this for a 90-degree rotation on Z, and its respective inverse is going to be, again, the transpose as we saw earlier in the slides. And so when we multiply these two by each other, we've seen that we get the identity. And you know what you can kind of do here is just see the way that this breaks down. So cool, pretty straightforward. Like again, this is just basic matrix multiplication stuff, and we're kind of faking the inverse by knowing that the inverse of a rotation in one direction is the opposite rotation in the other direction, but you can kind of see how these operate. So for 30 degrees, for 90 degrees, that's what we expect. So cool stuff, really useful to know that you can kind of inverse, you can undo, but you'll notice a lot of things. You'll notice something that in all of the cases that we showed, the inverse in this case was the transpose. And so these are a special class of matrix called a unitary matrix, where the transpose is equal to the inverse of that. And this is really, really useful to know about, because in taking the inverse of a matrix, an arbitrary matrix, can be a particularly complex or high. It's not a cheap calculation to do. There are fixed functions, there are fixed ways to get inverses, especially for 3x3 and 4x4. You know, it's not an arbitrary inverse of like 1,000,000 by 1,000,000, and those you have to use really different approaches for. But still, it's a lot more than having to just flip a bunch of things around. And so if you can use the transpose instead of the inverse, sometimes you can save a lot of performance in engine development. So in this case, let's just do the transpose, and we'll see for 30 degrees we get the exact same thing. For 60 degrees, we get the exact same thing as we did before, and same thing for 90 degrees. So in this case, right, we really just benefit from being able to use for rotational matrices the transpose instead of the inverse. And so, yeah, there's you can kind of see that the equivalent is actually true if you just look at the inverse itself. If we just look at the math of how to get an inverse for this particular matrix, you can see that the values actually look like the transpose, which is pretty neat, right? And all we have to do is just realize that in this case, the sign of the negative theta is equal to negative sign. And so if you just literally apply those equations, like, okay, throw a negative theta, say we take the top matrix, right, and we throw in a negative theta, this is what we get, and that is exactly the inverse. So yeah, very useful little trick. Definitely recommend using it in particular on the shader side. If you're ever doing inverses and stuff like that in GLSL or any shader language, you can imagine you'll save a significant amount of performance if you use transpose over inversing. And you do need to do that a lot when you're dealing with the rotations of normals and when you're doing the rotations from like one space to another. So yeah, awesome little review.